Welcome to The Explainer. Today, we're going on a seriously fascinating journey. We are going to trace the incredible engineering path of solar energy. Seriously, we're going to follow a single watt of power from the exact moment it's harvested by a photovoltaic panel, right through the incredibly complex power electronic interfaces, and finally out into our electrical grid. It's this massive, intricate puzzle that requires a delicate balance. We want to maximize power extraction, but we absolutely have to maintain the strict stability of our utility networks at the same time. Okay, so here's our roadmap for today. We'll be hitting 5 main stops: connecting solar to the grid, the quest for maximum power, how Perturb and Observe works, when solar confuses the grid, and finally, the dangers of islanding. To get us oriented, let's map out the whole system. What we have is an essential 2-stage cascade hardware configuration. This is basically the bridge between the PV array on one side and the utility distribution grid on the other. Power flows from the panels, hits a DC to DC converter, then a DC to AC converter, passes through a filter and a coupling transformer, and boom, it hits the grid. That entire middle section, that is exactly where the magic happens. All right, part 1, connecting solar to the grid. Let's talk about that hardware interface. So that middle section we just mapped out, engineers formally call that the power conditioning system, or PCS. You can think of the PCS as the literal brain of the entire operation. Its main gig is successfully controlling the active power flow that gets exchanged with the electric system. But here's what makes it an absolute game changer for modern smart grids. With the right setup, it lets the system simultaneously and independently control both the instantaneous active power, which, is the usable energy, and the reactive power, which is what keeps the grid stable. Now, it's pretty interesting to contrast the standard setup with the alternative. The conventional 2-stage cascade setup we just talked about uses one stage for boosting voltage and tracking maximum power, and a completely separate second stage for feeding AC power to the grid. On the flip side, you have classical single-stage topologies that try to just do it all, boosting and AC conversion, in one single step. But the 2-stage configuration is by far the most commonly used solution globally. Why? Because breaking it up offers this really essential extra degree of freedom in how you control the operation. Of course, there's always a catch, right? To get that independent control, engineers have to swallow some pretty notable trade-offs. The 2-stage arrangement actually suffers from lower power conversion efficiency, simply because the power is forced to pass through 2 distinct processing stages. It also has slightly lower reliability because you're adding more fully controlled switches and a chopper circuit into the mix. And finally, because of that extra boost stage, the equipment itself is significantly bulkier and heavier. It's your classic engineering compromise. Moving right along to part 2, the quest for maximum power. We need to extract every single drop. Solar arrays require a huge initial investment, and they don't last forever, so squeezing every possible watt out of them is absolutely crucial. This is where the maximum power point tracking, or mppt controller, steps in. This specialized controller acts like a hawk, constantly sensing the real-time current and voltage coming from the PV modules. It takes that data and seamlessly adjusts the converter, specifically tweaking the duty cycle to lock right in on the maximum instant power available. It's constantly adjusting to perfectly match the output to the load. Which brings us to part 3, how Perturb and Observe works. Let's look at the algorithm behind the magic. To really get this, imagine the characteristic PV array power curve as a physical hill. There is one distinct peak where maximum power is achieved. The algorithm hunting for this peak is often called hill climbing, or Perturb and Observe. Picture the system like a hiker climbing a mountain in super thick fog. They can't actually see the peak, but they can feel if their next step is taking them uphill or downhill. The algorithm perturbs, meaning it slightly tweaks the operating voltage, and then checks if that little step pushed the power output higher up the curve. It's a remarkably simple logic loop. The system nudges the voltage by modifying the duty cycle. Then it observes, did the power go up? If yes, great, the system knows it's hiking uphill, so it keeps stepping in that same direction. But if the power drops, it means it either stepped over the peak or is walking backwards down the hill. So the next perturbation logically has to be in the opposite direction. A massive reason this specific algorithm dominates the industry is its pure elegance. Think about it. It only requires a single voltage sensor to read the PV array voltage. That's it. Because it's so incredibly simple, it is a hugely cost-effective and, naturally, a wildly popular solution for the engineers building these grid-connected systems. The controller is just endlessly running this loop. It senses the voltage and current, calculates the power, compares it to what it was a split second ago, decides to bump the reference voltage up or down, and then starts all over again. And because it's locked in this continuous cycle, the operating point doesn't just find the peak and freeze. Actually, scratch that. It never freezes. It continually oscillates, just kind of wobbling right back and forth over that absolute maximum peak point. Now, while Perturb and Observe is dirt cheap and super easy to implement, it's not totally perfect. Its convergence speed, how fast it finds that peak, can vary. Compare that to something like fuzzy logic control, which is lightning fast but comes with a massively high implementation complexity. Once again, we're looking at a classic trade-off between keeping things simple and going for high-speed precision. All right, part 4, when solar confuses the grid. This is where we see some unexpected plot twists. So this leads us to a highly counterintuitive question. It's one that catches a lot of people, even some seasoned power professionals, completely off guard. We hear all the time that putting solar on the grid supports the grid, right? But does distributed solar generation actually always support utility voltage? Believe it or not, the answer is no. If you look at a standard feeder voltage profile, turning a distributed solar generation unit on can actually cause the voltage to drop significantly further down the line. Sounds crazy, right? Let's break down exactly why this happens. It all comes down to how the grid's automated hardware sees the network. Because the solar input visually reduces the observed load at the line drop compensator, which is basically the grid's voltage sensor, it accidentally tricks the regulator. The regulator gets totally confused, thinks the load is way lower than it is, and sets a voltage much lower than what's actually needed to maintain service at the far end of the line. As the research bluntly points out, this is the exact opposite of voltage support. And it's not just sustained voltage drops we have to worry about either. Step changes in solar output, like, say, a giant cloud suddenly rolling over a massive solar array, can cause rapid, chaotic voltage fluctuations on the feeder. If a solar generator's output bounces around frequently enough, it pushes lighting loads past standard annoyance thresholds. You'll literally start seeing a noticeable, highly irritating flicker in the lights of regular consumers. Finally, part 5, the dangers of islanding. What happens when the grid fails? Islanding is a spectacularly dangerous scenario. By definition, it happens when a local generator is no longer operating in parallel with the utility system. Let's say a tree falls and completely severs the main grid power line, but the local solar panels keep pumping out juice. It effectively creates this localized island of energized circuits feeding active power into external utility lines that everyone assumes are totally dead. Utilities strictly forbid this from happening, and for very good reason. First off, having live islanded generators makes it incredibly dangerous for utility workers trying to fix the downed lines. Second, it totally sabotages automatic reclosing, which is the very first trick a utility uses to try and automatically snap the power back on. And lastly, that isolated solar generator just cannot maintain acceptable power quality on its own. The voltage and frequency can swing wildly out of control, which can actually fry the electronics of neighboring houses. Because of all this, any properly designed grid connection has one absolute non-negotiable imperative: rapid interconnect protection. The entire job of this protection is to instantly detect asynchronous operation. The second it realizes it's no longer syncing with the main grid, it has to immediately sever the connection, trip the circuit. And this has to happen in mere fractions of a second, so those automatic utility safety systems can function properly. So as we wrap up this explainer, we've seen just how insanely complex the journey of a single watt truly is. From power conditioning systems managing efficiencies, to clever algorithms hunting for peak power in the fog, all the way to the critical fail-safes preventing grid confusion and deadly islanding, it leaves us with a really high-stakes engineering question to ponder. As our infrastructure heavily shifts toward distributed generation, how exactly will future smart grids manage to balance this relentless drive for maximum solar extraction with the absolute, uncompromising safety of our utility networks? It's a huge puzzle for sure. Thanks so much for joining me on The Explainer.